Assalamualaikum warahmatullahi wabarakatuh. My name is ASHIKA binti MARZAIRI.
My name is SYAZWANIE binti ZAINON.
We are from Mathematics 3 and we will be presenting about our task 3, which is a presentation for subject algebra. For my presentation, I will be explaining about my report writing, which is titled Solving Daily Problems Regarding Navigation of Walking to the Hypermarket. At first glance, walking to a store seems like a mundane, almost thoughtless activity. We step out of our doors, we follow paths, we arrive, but beneath the simple act of complex web of mathematical principles that humans have been trying to approach for centuries. Before I dive into the data, I want to address why I choose this specific topic. People often ask me why I didn't choose something that's more grand and academic. The truth is, I've always felt that mathematics suffers from a PB problem. We often treat it as a series of cold, abstract numbers trapped inside a textbook, disconnected from the air we breathe and the ground we walk on. I chose this topic because I wanted to find the hidden geometry in my life. I wanted to prove that we decide to take shortcuts across a field or choose to cross a street at a specific angle. We aren't just moving, we are intuitively performing vectors calculus. I wanted to take the genius of mathematicians like Oliver Heaviside, the man who developed vector calculus, and applied it to my neighborhood. Heaviside once said that the beauty of vectors lies in their ability to simplify the complex geometry of the real world. And that is exactly what I set out in my report. So, Wani, what about you?
The main reason I chose this topic is because I wanted to connect mathematics with something modern and realistic. Nowadays, automation technology is developing very quickly. We can see robots being used in hospital, warehouse, airports, and even restaurants. In some restaurants, service robots are used to deliver food from the kitchen to the customer's table. When I thought about this situation, I realized that behind this simple movement, there must be a mathematical principle that guides how the robot to move accurately and efficiently. That is when I decided to explore vector analysis in this context. Many students, including myself, before this sometimes see vectors as an abstract concept that only exists in textbooks. We learn about magnitude, direction, components, and sometimes the product, but we do not always see how this idea applies in real life. Through this project, I wanted to show that vectors are not just theoretical ideas. They are actually used in robotics, navigation system, and many modern technologies. This makes the topic feel more meaningful and practical to me. To understand the topic better, we first need to understand what a vector really is. A vector is a quantity that both magnitude and direction. For example, if I say a robot moves 5 meters, that only tell us the distance. But if I say the robot moves 5 meters forward, that includes direction. That is displacement, which is a vector. Similarly, force is also a vector because it has strength and direction. When a robot motor pushes it forward, the force applied has a specific direction. Without direction, we cannot fully describe the movement.
So I'm gonna get through the concept in my report writing. I start by laying the foundation of what makes a vector. A vector To understand movement, we must understand the positions. In mathematics, every journey requires a point of origin. This is our fixed starting point on the Cartesian plane with the coordinate 0, 0. From this point, we can define two very different types of vectors, the position vectors and the relative vectors. A position vector is essentially a GPS coordinate for a single point. It tells us the location of a point with respect to our origins. We represent it in the form of xi plus yi, where the I is the unit vector for the horizontal x directions and the j is the unit vectors for the vertical directions. However, in my writing, I focus heavily on the vector. If you are at a point A and you want to get to point B, you aren't necessarily worrying about the origins of the city. You only care about the point B to where you are standing. Mathematically, we must find this by subtracting the positions of vectors of our starting point from the vector to our directions. This leads us to the resultant path. When we break this movement into their horizontal and vertical components, we gain two pieces of information that are vital for any navigators. First, we get the magnitude, which is the shortest possible distance or displacement, as we say, between the 2 points. Second, we get the directions, which is the specific angles or bearing you must follow to reach your target. This is the B line, the perfect path that minimizes the time and energy. Wani, what is your real life problem about?
In my project, I imagine a scenario where a robot starts at the kitchen and needs to deliver food to a specific table. However, the restaurant environment is not empty or perfectly straight. It is a dynamic environment. Customers may walk around unexpectedly. The robot cannot move in a straight line. It must constantly adjust its direction. Every adjustment means a change in displacement vector. So instead of having one simple movement, the robot's parts become a combination of multiple vectors. This is where vector analysis becomes very useful. By breaking down the robot movement into components, we can understand how it reached its destination, even when the part is not straight. The concept of resolving movement into horizontal and vertical components helps us visualize how the robot adjusts left, right, forward, or slightly backwards before reaching the table. Even though the actual movement looks smooth in real life, mathematically it can be described as a series of connected vectors. Another important aspect of this project is force. In order for the robot to move, its motor must generate force. However, the force applied is not always perfectly aligned with the direction of displacement. For example, if the robot needs to slightly turn to avoid a customer, part of the vector contributes to forward movement and part contributes to sideway motion. This shows that not all applied force directly help the robot move towards its final destination. Some of the energy is used for steering or adjusting direction. This concept is important when discussing efficiency. In real-world robotics, efficiency matters a lot because it affects battery life and operating costs. If a robot constantly applies force in direction that do not contribute to forward motion, it will waste energy. Vector analysis allows engineers to measure how effectively force is being used.
The significance of this project goes beyond restaurant robots. Vector analysis is widely used in many industries. For example, self-driving cars use vector to calculate direction, speed and turning angles. Drones use vector principles to maintain balance and adjust their position in the air. In aerospace engineering, vectors are used to analyze force acting on aircraft and spacecraft. Even in computer graphics and video games, character movement is controlled using vector calculation. This shows that what we learn in algebra is actually foundational knowledge for many advanced technologies.
Our main challenge is to calculate the work done during a delivery to evaluate the robot efficiency. This efficiency depends heavily on the angle between the force vector and the displacement vector. By using the dot product, we can determine exactly how much of the motor's power contributes to moving the robot forward rather than being wasted. Now, let's look at the mathematical methodology. We use a 2D Cartesian coordinates system where the robot starts at point A, 0, 0 and the target stable 28A at point B, 4, 3. All our units are standardized in meters, newtons and joules. To reach the destination, the robot takes a specific part consisting of 4 movements. First, it moves 2 meters along the x-axis. Second, it moves 1 meter in x and 2 meters in y. Third, it adjusts by moving 1 meter in x and 1 meter backward in y. Finally, it moves 2 meters straight along the y-axis. By summing these factors, we find the net displacement, which is 4i plus 3j. Using the Pythagorean theorem, we can calculate the total magnitude of displacement to be 5 meters. The robot applies a total force of 30 Newton to overcome friction and carry the train. Because of obstacle avoidance, this force is applied at angle of 20 degrees. We resolve this into horizontal component, Fx 28.19 Newton, which push the robot forward. Vertical component, which is Fy, is 10.26 Newton, which help with sideways steering. Finally, we calculate the work done by substituting our value into the dot product formula, which is 28.19 times 4 plus 10.26 times 3, and the result is 143.54 joules. When we compare this to the maximum theoretical work of 150 joules, we can see that the actual work is lower. This confirms that energy is being used to overcome resistance and navigate adjustment.
So now I'm going to get through the real-world simulation I've talked about in my report writing, which is the real-world simulation from IPG-Pelajar to Pantai Timur Hypermarket. To demonstrate these theories, I applied them to real-world scenarios involving a student at Institut Pendidikan Guru, Kampus Kota Baru. The goal was simple: walk from the campus gate to the Pantai Timur Hypermarket. In my model, I labeled the campus gate as our point of origins with the coordinate 0, 0 and the hypermarket as point B. Now, theoretically, the shortest path is a straight vector OB, but the real world is rarely that kind. In these specific scenarios, a busy street acts as a major obstacle. You cannot simply walk through the traffic. Therefore, the student must first cross the road to reach the safe point, which I labeled as A. Only after reaching point A can they proceed to the final destination, which is point B. In my report, I used data from Google Maps to simulate this to find vector OA, the path to cross the road. I identified the linear distance as 50 meters and the direction as 90 degrees. Using the components formula where x is equal to cos theta and y is equal to r sine theta, I calculated that the horizontal component was 0 and the vertical component was 15. This gave us the vector OA, which is vector OA equal to 0i plus 50j. The horizontal distance was 1,539.19 meters, where we add the crossing of the road to the walk down of the street. We use vector additions. Vector OB is equal to vector OA plus vector AB. By the end of the simulation, my writing concludes that the vector representing the shortest distance between IPG-KKB and the hypermarket is vector OB is equal to 1,539.19i plus 2,000j with a magnitude of 1,540 meters. While these numbers might seem small on a page, they represent every step, every breath, and every second of that student journey.
Amber, what is the strength of your report?
Okay, that's a great question. The primary strength of my report is the advantage of using vectors is precision and efficiency. In a real world where we are constantly rushing finding a resultant displacement vectors allows the navigator to find the most direct route possible. This is not just a math exercise. It is a way to minimize the expenditure of time and energy. Furthermore, vector modeling is incredibly powerful because it allows us to predict outcomes where the multiple forces are acting at once. For example, a student isn't walking. They might be walking against a heavy wind or navigating a slope. Vectors allow us to account for these forces and still find our ways.
What is the weakness of your report?
Even though I have a lot of strengths, however, I do have to admit that I also had so many weaknesses and limitations of this model in my writing. The most significant limitation is that the mathematical model often assumes ideal conditions that simply don't exist in reality. Vectors provide a straight line path, but a vector cannot tell you that there is a fence in your way, or a restricted area, or a campus building that you cannot walk through. Another weakness is that my model, like many vectors model, operates in 2D spaces. It assumes the world is a flat map. It omits environmental factors like terrain elevation. Walking up a hill is much harder than walking on a flat ground. Even if the displacement of a map looks the same, there is also challenges of human error. In my report, I noted that while we can calculate the angle of exactly 90 degrees on paper, it is almost impossible for a human to measure that accurate while walking down the street without a specialized equipment like a high precision GPS, while we are limited by our own senses.
There are several strengths in this project. One of the main strengths is that it connects abstract mathematical concepts to real-world application. Instead of seeing vectors as simple arrows on paper, we can imagine how they represent actual movement in physical space. This improves understanding because it encourages visualization. When we imagine a robot moving inside a restaurant, it becomes easier to understand how direction and magnitude work together.
Another strength is that the project promotes interdisciplinary thinking. It combines mathematics with elements of physics and engineering. Robotics is not just about programming, it also requires strong mathematical foundation. By exploring this topic, I learned how different fields of knowledge are connected. Mathematics is not isolated from technology. Instead, it supports and strengthens technological innovation.
So what are your limitations in your report?
This project also has limitations. The most obvious limitation is that it simplified a complex real-world system. In reality, autonomous robots use sensor, camera, and artificial intelligence or advanced algorithm to make decisions. My project only focused on the mathematical foundation using vector analysis. It does not include programming or machine learning aspect. This means that the model does not fully represent the complexity of actual robot navigation system. Another limitation is that the scenario is simplified into two-dimensional movement. In real-life environment, especially in advanced robotics, three-dimensional analysis may be required. Additionally, real-life conditions are unpredictable. Customer may suddenly change direction, objects may move unexpectedly, and mechanical factors like friction or battery level may vary. My project assumes control conditions to make the analysis clear. Why this makes the explanation easier to understand? It reduces realism. Even with this limitation, I believe the project successfully achieved its purpose. The main objective was to demonstrate how vector analysis can explain motion and force in a practical situation. By simplifying the environment, I was able to focus on the core mathematical ideas without being distracted by too many technical details. Sometimes simplifying a problem helps us to understand the fundamental principle more clearly. From a personal perspective, this project has changed how I view mathematics. Before this, I sometimes thought algebra was difficult and abstract. Through the project, I realized that mathematics is actually a powerful tool for modeling real-world systems. It provides a logical and structured way to analyze problems. I also learned that understanding concepts deeply is more important than memorizing formulas. When I understood how vectors describe motion in a robot navigation, the topic became much more interesting and easier to appreciate. If I could improve this project in the future, I would like to add a visual simulation to show the robot's movement more clearly. Seeing the part animation would make explanation more engaging. I would also explore different routes and options to compare which part is more efficient in terms of energy use. Furthermore, integrating basic artificial intelligence decision-making processes could make the project more advanced and closer to real-world robotic systems. In conclusion, this project demonstrates how vector analysis plays an important role in understanding motion, force, and navigation in autonomous systems. By applying vector concept to a restaurant service robot scenario, it shows that mathematics is not just theoretical knowledge, but a practical tool used in modern technology. Although the model is simplified, it effectively illustrates how displacement and force vectors interact to determine movement and efficiency. Most importantly, this project helped me appreciate the relevance of algebra in real-life innovation and technological development.
While the mathematical model has its limitation, its inability to see a new trespassing signs or step hill it remains the most precise method we have to understand where we are in relation to the world around us. Mastering these calculations has improved my mathematical literacy, but more importantly, it has given me an appreciation for the hidden geometry that governs my life. We often think of science and math as things that happens in labs or universities, but as I've tried to show in my report, math happens on the street corner. It happens at the campus gate. It happens on the way to the hypermarket, and it is the language of our movement. Mastering these calculations has improved my mathematical literacy, but more importantly, it has given me an appreciation for the hidden geometry that governs my life.
Thank you for watching our presentation.